Build a local AI agent that remembers context, searches demo docs with RAG, and calls mock tools through MCP. Let's begin with Build the Agent Memory Loop. This tutorial builds a local AI agent workflow with 3 abilities. It can search demo documents using a small RAG pipeline. It can remember and recall simple local preferences. It can call mock tools through a local MCP server. The working result is an agent loop: remember, retrieve, use a tool, and answer. The key lesson is how memory, RAG, MCP, and tools fit together. Every code block has one clear responsibility. That sets up how the pieces connect. Start with the architecture before reading code. The AI code editor host runs the agent conversation. The MCP client connects that host to a local demo server. The server exposes mock tools for memory, document search, and simulated planning. RAG brings trusted local demo knowledge into the answer. Memory brings useful past context into the next step. Tools let the agent perform controlled local actions. With how the pieces connect in mind, the next piece is what memory adds. RAG answers from documents. Tools perform controlled actions. Memory keeps useful context across steps. For example, the agent can remember that the viewer prefers simple explanations. Later, it can recall that preference before writing the final answer. This makes the agent feel more consistent. But memory must be scoped, limited, and reviewable in real systems. That idea leads directly to what RAG adds. Memory is not the same as knowledge search. RAG searches documents for task-specific evidence. It helps the agent answer from source material instead of guessing. In this demo, the documents are fictional and local. The agent can search a return policy or support playbook. Then it uses retrieved context while writing the answer. That is the retrieval part of the agent workflow. Once what RAG adds is clear, what MCP adds becomes much easier to understand. MCP is the connection layer between the agent host and external capabilities. In this tutorial, external means local demo tools. The server describes what tools exist and what inputs they need. The host can then make tool calls when the agent needs them. This separates the agent conversation from tool implementation. It also makes the tools reusable across workflows. For this build, MCP connects memory, RAG, and a mock action tool. From there, the next practical step is project setup. The setup creates a small TypeScript project. The MCP SDK provides the server and transport pieces. Zod validates tool input schemas. The SRC folder holds the server, memory, and RAG code. The data folder is available for local demo files. The .cursor folder holds project-level MCP configuration if your host supports it. Keep the first version small so each failure is easy to debug. This sets up the next important point: package scripts. The scripts control how the server runs. Dev runs TypeScript directly during development. Build compiles the server to JavaScript. Start runs the compiled server. A local AI code editor host usually launches the compiled file. That is why rebuilding after edits matters. The runtime path should match the MCP config later. That sets up TypeScript Output. The TypeScript config connects source files to runtime files. root_dir keeps source code under SRC. out_dir sends compiled JavaScript to dist. Node next supports modern Node module imports. Strict mode catches common type errors early. This config makes the server easier to launch from MCP settings. It also keeps generated files separate from source files. With TypeScript Output in mind, the next piece is local demo documents. The RAG tool needs a knowledge source. We start with 2 fictional local documents. One document is a demo return policy. The other is a sample support playbook. Each document has an ID, title, and text field. This is enough to teach retrieval without using private files. Later, the same pattern can point to approved sources. That idea leads directly to memory data shape. Memory needs structure before it becomes useful. Each entry has a key and value. The scope tells us the memory belongs to this demo user context. The timestamp helps show when the memory was updated. The local array keeps the demo simple. Because it is in memory, it resets when the server restarts. That is acceptable for a tutorial and easy to verify. Once memory data shape is clear, write demo memory becomes much easier to understand. The remember function creates one local memory entry. It receives a key and value from the MCP tool. It adds a demo_user scope. It adds a timestamp for traceability. Then it pushes the entry into the local memory array. The output is the stored entry. That makes the memory write easy to inspect. From there, the next practical step is recall demo memory. The recall function searches local memory by keyword. It checks both the key and the value. This is intentionally simple for the demo. It lets the agent ask what it already knows before answering. For example, it can recall a preferred explanation style. The output is a list of matching memory entries. This is the memory read side of the agent loop. This sets up the next important point, demo embeddings. RAG needs a way to compare meaning. A real system would use an embedding model. This tutorial uses a tiny deterministic demo embedding. The vocabulary turns selected terms into a small vector. The dot function gives a simple similarity score. This is not production search. It is a readable way to understand what embeddings do. That sets up build the demo vector index. After documents can become vectors, they need an index. The index stores each document with its demo vector. When a query arrives, it becomes a vector too. The search function scores every document against the query. Then it sorts the results and returns the best matches. This is the local demo version of vector search. The same concept scales to real vector databases later. With build the demo vector index in mind, the next piece is create the MCP server. The MCP server is the bridge between the agent host and our code. It imports the server and stdio transport from the SDK. It imports ZOD for tool input validation. It also imports the memory and RAG helper functions. The server name identifies this local demo tool provider. At this point, the server exists but has no tools registered. The next scenes add those capabilities one by one. That idea leads directly to Tool 1, Search Demo Docs. The first MCP tool exposes RAG retrieval. It receives a query string from the agent. It calls search docs to retrieve local demo documents. Then it returns the ranked matches as JSON text. The model can use those results as context for the final answer. This keeps retrieval separate from answer writing. That separation is the heart of RAG architecture. Once Tool 1, Search Demo Docs is clear, Tool 2, Remember Preference becomes much easier to understand. The second tool writes local demo memory. It receives a key and value from the agent. It calls the Remember helper. Then it returns the stored memory entry. This lets the agent preserve a small preference for later steps. The tool name includes mock to avoid confusion with production memory. That naming habit is useful in demo projects. From there, the next practical step is Tool 3, Recall Memory. The third tool reads local demo memory. It receives a query from the agent. It calls the recall helper. Then it returns matching memory entries. This gives the agent past context before it writes the response. In the final test, it will recall the preferred explanation style. That turns memory into useful behavior. This sets up the next important point, Tool 4, Simulated Plan. The fourth tool demonstrates action without external side effects. It receives a topic and owner. It returns a simulated follow-up plan as text. It does not create a real ticket, task, email, or database entry. This shows how action tools behave while keeping the tutorial safe. For production, action tools need stronger controls. For learning, simulated action is enough. That sets up connect through stdio. The tools are registered, but the server still needs a transport. Stdio lets the local host launch the server as a process. The server and host exchange MCP messages through input and output streams. The main function connects the server to this transport. If this step fails, tools will not appear in the host. Keep stout clean because the protocol uses it. This is the final server-side wiring step. With connect through stdio in mind, the next piece is Project MCP Config. The Project MCP Config tells the host how to start the server. The server name matches the local demo server. The transport type is stdio. The command is node. The argument points to the compiled dist/server.js file. After changing server code, rebuild before testing again. A wrong path is one of the most common setup mistakes. That idea leads directly to build and inspect tools. Before testing the agent, compile the server. The build creates dist/server.js. Then enable or refresh the local MCP server in your AI code editor host. You should see 4 mock tools. If tools do not appear, check the compiled file path first. Then check the server logs and import errors. Tool discovery proves the host can see the MCP server. Once build and inspect tools is clear, test the full agent loop becomes much easier to understand. The test prompt forces the agent to use all 3 ideas. It first stores a preference in memory. Then it searches the demo documents with RAG. Then it recalls the memory before answering. Finally, it calls the simulated planning tool. A good demo answer should mention retrieved context and remembered preference. That proves the pieces are working together. From there, the next practical step is expected tool call trace. The expected trace is easy to follow. First, the agent calls mock remember preference. Second, it calls mock search demo_docs. Third, it calls mock recall memory. Fourth, it calls mock create demo_plan. Then it writes the demo final answer. This trace is more important than the exact wording of the answer. It shows the agent is using the system design correctly. This sets up the next important point: add a simple guard. Even local tools should teach safe design habits. This helper rejects inputs that mention production, real customers, or live databases. It is not a complete security layer. It is a small teaching guard that protects the demo boundary. The important idea is server-side validation. Do not rely only on prompt instructions for tool safety. The server should enforce its own limits. That sets up memory risk. What to limit? Memory can improve the user experience, but it also creates risk. Do not store everything the user says. Do not store sensitive personal data by default. Use scopes, retention rules, and clear review paths. Separate short-term session memory from long-term memory. Make memory visible and editable where possible. Good memory design is selective, not unlimited. With memory risk, what to limit in mind, the next piece is RAG risk, what to verify. RAG can reduce unsupported answers, but it is not magic. Retrieval may choose the wrong document. The source may be outdated. The model may overstate what the source says. Add citations when the source matters. Test missing answer cases, not only easy questions. RAG systems need evaluation before trust. That idea leads directly to tool risk, what to control. Tools are where agents become powerful. They are also where risk increases. Read tools are usually safer than write tools. Action tools need approval gates and audit logs. Tool input should be validated on the server. Credentials should be scoped and limited. Production tools need monitoring and safe failure handling. Once tool risk, what to control is clear, common beginner mistakes becomes much easier to understand. One mistake is mixing memory and RAG into one vague concept. Another is building tools before designing schemas. A third is using action tools too early. A fourth is testing only the happy path. Beginners also forget to rebuild before testing MCP changes. Some assume memory makes the agent intelligent by itself. The better approach is small tools, clear data flow, and visible traces. From there, the next practical step is production upgrade path. The demo teaches the pattern, not production readiness. A real system would replace toy embeddings with an approved embedding model. It would use a real vector database or managed retrieval service. It would store memory with consent, retention, and deletion controls. It would add authentication, rate limits, audit logs, and approvals. It would test tool misuse and prompt injection cases. Production is an engineering program, not one extra code block. This sets up the next important point, final content recap. The local demo agent now has 4 connected abilities. Memory stores and recalls useful context. RAG searches fictional local documents for evidence. MCP exposes those abilities as mock tools. The agent uses tool results to produce a better answer. The full loop is remember, retrieve, act safely, and respond. The next improvement is stronger evaluation and safer approval design. That is how memory, RAG, MCP, and tools come together. To wrap up, here is the key takeaway. You now have a structured overview of build an AI agent with memory, RAG, MCP, and tools explained step by step. Review the core ideas, connect them to examples, and revisit concepts like build the agent memory loop, how the pieces connect, what memory adds when practicing. Subscribe to Easy Machine Learning Guide if you want to learn AI through simple explanations and real industry examples.